SwayamPrabha. Digital India. Educated India.
We started talking about eutectoid last 2-3 classes. We will try to continue today and then go into martensitic transformation, because that is a kind of an offshoot of eutectoid transformation that you get. So there is one aspect about eutectoid transformation which we have been seeing yesterday, is about what is the kinetics of it. Yesterday we considered it partially last class. Let us try to continue this, though it is slightly off from our class. As you all know that a eutectoid transformation, as long as you take a composition of that sort, we have seen that it is the driving force that you get for such a transformation, which can be seen from a free energy composition diagram, which we have seen. Let us say you take a case like that you have a certain driving force at a given temperature below the eutectoid transformation. This undercooling, which translates to this driving force, is actually drives the whole reaction. This we have seen it even in the eutectic. So I thought let us just recapitulate once again, because if you look at eutectoid transformation as some phase, let us say call it as alpha, beta, and this is beta coming out of a gamma something. We can take it as an iron carbon system or any other system. If you take it, we see that this growth of this lamellae depends on the atoms joining from gamma to both beta and alpha, right. So when atoms from gamma come and join the beta, and we know that beta is, let us say, a B rich phase, alpha is a rich phase. So you need excess B atoms to come and join beta and excess A atoms to come and join alpha, and then you will see the whole thing will grow far. This how a gamma can supply excess atoms of B to beta and excess atoms of A to alpha is what you can see again if you draw a common tangent between gamma and alpha and gamma and beta. So if you look at this, call this as gamma, this as alpha, this as beta, and simply draw a common tangent between let us say I am drawing a common tangent between gamma and alpha. That means the moment I have gamma in equilibrium with alpha, what is the composition of gamma which is just in front of alpha? The composition of gamma which is just in front of alpha, which is in equilibrium with alpha, is given by this common tangent composition. Am I right? So where gamma is in equilibrium with alpha, let us not bother about what is the composition of alpha in equilibrium with gamma, but if you look at what is the composition of gamma in equilibrium with alpha, this is what you will get. And similarly, if you look at what is the composition of gamma in front of beta, again we draw another common tangent between the beta and the gamma, and you get another composition here. We call this as C gamma alpha, we call this as C gamma beta, right. And we can see now that the composition of gamma in equilibrium with alpha has more B atoms. If you say percentage B is increasing in this direction, so here you have more B atoms than here. As a result, you will see that the B atoms will start moving in this direction, and that gradient, if you want to consider it, that gradient can be given by C gamma alpha minus C gamma beta divided by lambda by 2, because this whole thing is lambda. am I right? That is what we call it as interlamellar distance. The center of one beta to center of another beta is what is the interlamellar distance, and this distance that we are talking about is half of that interlamellar distance. So if that is the case, this is what is the dc by dx. Am I right? I put this x as small. Again certain notations one has to remember. X capital usually means mole fraction, okay. So put x as small, let us say. In fact, some people prefer to write x here rather than c. For composition, either you can use c or x depending on whatever you want. As long as you are consistent in one of the notation, you can use x or c there. So if this is the case, then we know the flux is J is minus d dc by dx. So again coming back to what we have done in eutectic is exactly similar. So it is this which drives this, and at a given temperature, if this eutectoid transformation is happening, if I say that I have taken this alloy gamma, brought it to this temperature and holding it there at that temperature till the transformation is over. If I am saying that at that temperature these two are fixed, that means this is fixed, and that if it is fixed and if the lambda is fixed, lambda basically depends on the undercooling. It is undercooling which decides the lambda, and once the lambda is fixed, the concentration gradient is more or less fixed, and once the concentration gradient is fixed and d is also fixed for that particular temperature, you would see this grows at a particular rate. So the growth rate is dependent on the temperature, that means the undercooling, in two ways. One, the undercooling decides the d, the undercooling also decides the dc by dx, because the undercooling is what decides this. And how do I see that? I can see it easily if I extrapolate this, this is what? This composition. If I call this as gamma, if I call this as alpha, and if I have some beta here, let us say, yes, this is the composition of gamma in equilibrium with beta, because it is that solvus line or that transformation line which is a gamma to beta transformation line, which is what I am extrapolating. So this line is actually gives you composition of gamma in equilibrium with beta at all temperatures. So because I am extrapolating that to a lower temperature, then I can say that this is nothing but C gamma beta, and similarly this would be C gamma alpha, because this is the line which talks about composition of gamma in equilibrium with alpha, right. So if you use the same logic as we have used in eutectic, so this difference between these two decides the delta C here, and because that decides delta C, in principle we can say the dc by dx is decided by that, and once you identify that, you can say that the growth rate of this eutectoid depends on that. But keeping in mind that there are two points, two parameters here which kind of counteract each other. One is that the dc by dx in principle increases with undercooling. In dc by dx also there are two, one is dc, another is dx. Dx here is our lambda by 2. What happens to lambda by 2 as I increase undercooling? It decreases. And what happens to delta C? Increases. So you see that the numerator is increasing, the denominator is decreasing, am I right? So that means this fraction increases with undercooling, but at the same time the D, again diffusivity, as I increase undercooling, diffusivity should go down. So this growth rate is again a combination of the temperature, which is where diffusivity decides that, and the dC by dx. So, a combination of these two will tell you that the growth rate will reach a maximum somewhere at in the intermediate temperature range. It will not be highest near at the eutectoid transformation temperature. In principle, growth rate will be 0 because dC is 0, because you can see this difference at the eutectoid temperature is 0. That means C gamma alpha minus C gamma beta is 0 at this temperature, and it is that which is driving the which is the part of the gradient, and if there is no gradient, there is no diffusion. So, as a result, you will see that at the eutectoid, you will see, if I now plot the growth rate G as a function of undercooling, you would see the it would be something like this. At 0 undercooling, what I mean by 0 undercooling? At the eutectoid transformation temperature, this will be 0, and it would again go down when you go to higher undercoolings, because the temperature is going down where the D is going down, though this is increasing. So, that is why again it would be a combination of two curves, one which is nothing but the diffusivity. So, diffusivity is decreasing with increasing undercooling, and the dC by dx is increasing with increasing undercooling. So, if I say this is dC by dx and this is diffusivity, one is increasing with increasing undercooling, another is decreasing with increasing undercooling. So, as a result, a combination of these two, you would see the growth rate will be like this. This is growth rate, this I am sorry, if G is not free energy. So, growth rate G, whatever you want to call it, you call it as velocity V, growth velocity. In fact, incidentally, people also use G in solidification as a gradient. Temperature gradient is also given the same term. So, same term you get in different connections. So, if you call this as a growth velocity, so growth velocity would be having a similar curve. So, because we are talking about this, I thought you should also have an idea of this. Now, in addition, we also talked yesterday about, in the last class, about the morphology of alpha. You see, if you take an alloy of this particular composition, we also said yesterday that if I take this alloy, undercool it below this temperature, you directly get a perlite or a bainite depending on where you are with respect to that temperature. So, if I am doing it here, let us say I am closer to the eutectoid temperature. So, that means in a TTT diagram, you are closer here to the eutectoid temperature. So, because you are closer to the eutectoid temperature, this particular alloy, if I undercool it below this particular temperature, then it would give me a perlite rather than giving me a bainite. But if I take this alloy which is farther from the eutectoid composition, this alloy, if I can undercool, of course undercooling that alloy to that temperature is also not easy, because the extent of undercooling that I need to provide is very large. If I can somehow provide that undercooling, then you would direct and hold it at that temperature below that particular temperature, you would end up in a bainite, and that is what you see when I undercool it, hold it there, I would end up in a bainite there. Though there is a pro-eutectoid phase, no pro-eutectoid phase will come out during this undercooling, because you are cooling it fast, you are not allowing time for the pro-eutectoid phase. So, instead of any pro-eutectoid phase coming, straight away you come to a region, and that is why we said if your cooling rate is higher than what is decided by where this pro-eutectoid component reaches the TTT curve of the eutectoid, and if your cooling rate is higher than that, obviously you will never get a pro-eutectoid phase. If your cooling rate is smaller, then you will cut both these, then you will get a pro-eutectoid phase. And depending on where it is cutting, what is the undercooling that you are achieving, the pro-eutectoid phase also the fineness of the projectile phase is going to be decided. For example, if I use a cooling rate like this with respect to the projectile transformation temperature, what is called the A3. Now with respect to that, if I consider the undercooling for this is smaller, the undercooling for this is larger. So because the undercooling is larger here, if I am using this cooling rate instead of that cooling rate, here I will get a finer alpha. We are now talking about the projectile phase. So you would get a finer alpha here instead of what you get here. So that is why whatever we have talked in the last class about what is the difference between annealing and normalizing, if we extend this to a hypoeutectoid alloy, in a hypoeutectoid alloy you will see another difference, that you will have a coarser alpha in a hypoeutectoid steel if you do annealing, if you will have a finer alpha if you do normalizing. That is the second thing that we have talked about. Is the projectile phase amount will keep on decreasing as you increase the cooling rate. That is what we have seen, that you will see that the amount of projectile phase will keep on decreasing until you reach a cooling rate faster than this. Let us say you have a cooling rate, okay, we can even consider a case where I think in the last class I showed you that. So if you have a cooling rate something like this, then you would only get eutectoid phase. In principle one can, provided you have the CCT diagram, one can talk about what is the amount of eutectoid phase, and the higher the cooling rate, that is the reason why by looking at the microstructure, if you want to find out what is the composition of alloy, in fact in BTech labs possibly you would have seen people asking you, see the microstructure of the steel and tell me what is the composition. In principle, if it is a plain carbon steel, assuming that it is a plain carbon steel, that in principle we can do this provided we have an annealed microstructure. If you have a normalized microstructure, it will not represent the composition of the alloy, basically because whatever you get from the lever rule, because basically you are going to use the lever rule and from the lever rule find out the composition of the alloy. So if you have seen the microstructure, certain area fraction, you assume it to be equivalent to a volume fraction, convert it into a weight fraction, and finally put it find out what will be the alloy composition corresponding to that weight fraction using the lever rule. This is how you have to actually calculate if you want to really calculate based on the microstructure what is the alloy composition, because the microstructure only gives you area fraction, it will not give you weight fraction, and what the lever rule gives you only weight fraction, it does not give you any area fraction or volume fraction, isn't it. So you need to correlate these things so that finally you get the weight fraction, and that if you want to do it, the lever rule can be applicable only under equilibrium conditions, because it is coming from the equilibrium phase diagram, isn't it. So that means you need to use a very slow cooling conditions to be able to use a lever rule. So if I have used a normalizing and got a microstructure, normalized steel microstructure, this will not correspond to, let us say 0.6% carbon steel. If I take, in principle lever rule tells me how much of ferrite, 0.6% carbon steel, how much is the ferrite, 25%, it is 1/4 3/4, because 0.6 by 0.8, that is what it is. So if it is about 75% of eutectoid mixture and 25% of ferrite, and if I now take the same steel and do normalizing 0.6% carbon, you will not see 25% of ferrite, you may see 15%, you may see 20%, depending on the cooling rate that you have adopted. And if I see 20% and go back and calculate from the lever rule and then say 20%, because it is 20%, its composition is, let us say 0.5 or so, you are doing an error. The actual composition, if you do chemical analysis, it will not correspond to that. The reason is I have taken a normalized steel, okay. In a normalized steel, the volume fraction of the ferrite phase will not correspond to what is decided by the phase diagram. So these are the minor issues which you have to be very clear when you want to actually utilize the microstructures to understand the composition, because many people may not directly have analysis facilities, chemical analysis facilities to do a composition. So we tend to do simply see the microstructure and get an idea of the composition. And also one more thing that you need to know is the microstructure also is decided by if the alloy is not a binary but a presence of alloying elements present. The moment you have alloying elements present, the whole phase diagram changes. The phase diagram is driven by the presence of ternary and quaternary alloying elements. For example, you must have seen when you are talking about alloy steels how chromium changes the phase diagram, how nickel changes the phase diagram. Particularly you must have seen the gamma zone shrinks when you add chromium, okay, basically because it stabilizes ferrite, it does not stabilize austenite. So it dissolves into, it wants to dissolve into ferrite, it does not want to dissolve into austenite. So austenite shrinks, in fact around 18% or so the austenite region is very small. What is the austenite region in our phase diagram? Austenite region, if I want to draw, so if I have so this is the one, this is the austenite domain, and what do you call this temperature? What is it called? What happens there? Gamma to delta. What is gamma to delta transformation temperature denoted as? A4. It is A4 temperature. This is A3. This is A1, and obviously there must be A2 somewhere. Okay, so that A2 is the magnetic transition. Okay, so that A4, and that is what you can actually see how carbon stabilizes the austenite. The moment you add carbon, you see A3 is decreasing, A4 is increasing. As I add more and more carbon, you see the A3 is decreasing and the A4 is increasing. That means pure iron gamma is stable only between these two, 910 to 1400, whereas in around 0.8% carbon or so you can see it extends from here to here. Of course this is 0.18, this is 0.8, so there is a difference. So there is a scale difference. So once, as I know that basically these two are increasing, tell you that this field is increasing, and that means whenever a phase field expands, that means that particular element stabilizes that structure, and this is basically because the carbon wants to be in an FCC structure rather than in a BCC structure. So that is why the alpha it tries to depress, gamma delta also it tries to depress. So the stability range of the delta gets reduced and the stability range of alpha gets reduced, so that you get gamma. So that clearly tells you that carbon is a gamma stabilizer. And the same thing now if you add the chromium, you will see that this whole thing shrinks, this whole gamma field shrinks to a small domain like this, around 18% or so, or 20% if you add. So that is how, and nickel if you add it, this goes down further, which is a austenite stabilizer. So any austenite stabilizer will keep on shifting it down. So you can know from that how each one stabilizes anyway. So these things also are decided by the composition, so we need to know about it. Okay. The second issue is, if I take this alloy and then I am cooling it, the alpha that is forming here, what would be the morphology of that alpha? People usually see that whether the alpha forms there or alpha forms here. For example, if I have undercooled this alloy to this temperature, still you will have an alpha forming because it has not yet intersected this. So you will have an alpha forming even if you have cooled it below the eutectoid temperature, if you have undercooled it below eutectoid temperature, not simply cooled it. So if you have simply cooled it, by that time eutectoid transformation is already over. So if you undercool it to that temperature, you can still get alpha. What would be the morphology of that alpha when compared to that alpha which is coming somewhere here? And this is what a large number of people have studied, and they see that the moment you are the transformation temperature is closer to the A3, you will see if gamma is there, a grain boundary between gamma, you see this kind of precipitation, which is what is called grain boundary allotriomorphs. Which are more or less spherical kind of precipitates of alpha. The moment the undercooling is very high, and let us say somewhere here you see the alpha coming out, in such a case you see the alpha comes out as a platelets with semi coherent interfaces between the, here these are all incoherent interfaces. The reason is, if you look at the growth rates of a semi coherent interface and a coherent interface, if you look at the ratio of these things, the rate of growth, if you think of velocity of a coherent of a semi coherent interface and a velocity of an incoherent interface, at high temperatures the velocity of both of them is more or less similar, because the diffusion rates are very high at high temperatures. But at lower temperatures you will see that the incoherent interface moves faster, because if a semi coherent or a coherent interface has to move, it has to maintain the coherency with the matrix before it grows. So for example, whenever you look at a plate, this is a coherent or a semi coherent interface, whereas this side is an incoherent interface. You will see that this grows faster when compared to this. This incoherent interface can grow faster, that is why plates grow laterally, they never grow. So the thickness of the plate does not change during a precipitation reaction. For example, if I take a aluminum copper, you get a theta double prime disc. The disc thickness rarely changes much, but the disc grows laterally because of this. This growth is much faster than this growth, because if you want this growth to occur, then you need to maintain the coherency continuously. The continuity of the atomic planes has to be maintained, whereas here there is no need of such thing. So as a result, you see that at higher temperatures, if you take the ratio of, if I plot the ratio of, yeah, because whenever you are talking of coherency, coherency is on any particular plane. When nucleation is taking place, okay, a plate is nucleating on a matrix, let us say a theta double prime or something like that, nucleating on a aluminum matrix. So the 111 plane of the aluminum matrix acts as a nucleating site. So it is only that plane which is oriented with respect to some plane of the precipitate, whatever plane it is, and once you see that, so this is the precipitation, and then if you look at the both the sides, if it has to maintain coherency with another plane of this, there may not be a plane which is perpendicular to this which is also coherent with the matrix with the precipitate, you may not see that. So you will see that as long as one plane is enough, there is a orientation relationship, the interfacial energy is reduced. So overall the system wants to reduce the interfacial energy, so it reduces, so the nucleation has taken place. Now how about the growth? So there is no such coherency on these sides, and because there is no coherency on these sides, any of the plate like precipitate will always have an incoherent component plus either a coherent or a semi coherent. Initially it could be coherent, slowly it may lead up to semi coherent, and finally you would see that this whole thing grows as a plate. This retains that instead of getting converted into an incoherent interface here itself. If it has to grow this way, then it will finally get converted to incoherent. Instead the system would prefer a growth in this direction. That is why in many cases you see plates coming. Even for example aluminum silicon alloy, the silicon grows like needles. Even in the liquid to solid transformation also you see this happening, not only solid to solid. That is because whenever you look at any precipitate, for example a nucleus has formed something like this, or maybe initially you imagine it is like a cube, because silicon is silicon let us say is cubic in nature, diamond cubic. So some nucleus has formed, this nucleus has to now grow. The growth depends on the rate of atoms joining from the liquid to that silicon, and not only it depends on that, it also depends on which plane of these needs less number of atoms for it to grow. Each plane here, if I consider, we have talked about Wolff's plot, that there is a shape for the nucleus. Once I consider there is a shape for the nucleus, there are so many planes which are covering that nucleus. Out of all these planes, whichever plane needs less number of atoms per unit area for it to grow, that will be the one which grows faster. That means those are the planes which are loose packed planes will grow faster than the close packed planes. Close packed planes need more number of atoms. So at a given temperature the liquid is supplying atoms. When the liquid is supplying atoms, the rate at which it can supply atoms depends on the diffusivity, and once this diffusivity is fixed at a given temperature, then it cannot preferentially give more atoms to a particular plane and less atoms to another plane. So the plane which receives, okay, all the planes are receiving same number of atoms in a given time, but this particular plane which needs less number of atoms for it to grow by a small delta x will grow, because if you have planes like this, something like this, let us say, if this plane needs less number of atoms for it to grow, once all the necessary number of atoms come and join that within a particular unit area, it grows by a small delta x, which is maybe one monolayer. Similarly, within that particular time, the number of atoms that are required for this particular plane to completely get filled, if they have not reached, then this will not grow, isn't it? So like that you will see the growth morphology sometimes will be entirely different from the morphology. So that means this keeps on growing, these atoms keep on growing, whereas this does not grow. Finally you will see that the growth morphology may become like this. The nucleus morphology is this, the growth morphology is this. These planes have grown, whereas these planes have not grown. So you can see that at the nucleation stage what you see is different from after certain growth. This is because certain planes grow faster. Same thing here also, you will see some of the interfaces grow faster and some of the interfaces grow slower, and that is what you see in this particular case. So if I plot the velocity of incoherent by velocity of semi coherent, this ratio increases with higher undercooling. At very small undercooling, which is close to let us say 0, then the ratio is close to around 1. At high temperatures the ratio is close to 1, that means both incoherent and semi coherent can grow, and once that happens you end up in this kind of a thing, spherical, all directions the growth is like a isotropic growth, whereas here at high undercoolings such a isotropic growth is not possible, and as a result you see that one direction it grows, which is the incoherent direction, the semi coherent directions it does not grow, and as a result it gets elongated. So that is what we call it as a Widman-Stratton structure. So Widman-Stratton structures come into picture basically because of that. Okay. So this is how you would see different types of alpha coming out of the gamma just because of the growth rates being different at different temperatures, because of the necessity for a semi coherent interface to maintain the coherency. Okay. An incoherent interface need not have to maintain coherency, so as a result it can grow faster.
So why is it incoherent in this case and semi-coherent in this case?
That is what I am saying. If you are looking at a plate like this, the nucleation is only on this, the nucleation is not here. If the nucleation is not here, that means this plane, if I have certain planes in this, let us think of a case like aluminum alloys, we add TiB2 to nucleate aluminum, which is called inoculants. Have you heard of it? Grain refiners we call them. So once I add TiB2 to aluminum, aluminum is nucleating on TiB2. Where does it nucleate? Basal plane. Am I right? The basal plane of TiB2 has the same orientation, the same atomic packing with respect to the 111 plane of aluminum. So that means if I think there is a plate of TiB2 on which aluminum has nucleated, aluminum will nucleate like this in such a way that this is the 111 plane of aluminum on the 0001 plane of TiB2. Once it has nucleated, what about the other planes? If this is aluminum which has nucleated on it, let us say a small one which has nucleated on this particular plate, once I think that it is nucleated, okay, I should actually draw it this way. This is nucleated on a large surface, this is the TiB2 surface on which it has nucleated. What about this plane? This plane which is perpendicular to 111 plane, the plane which is perpendicular to 111 plane is some other plane, is not it? You can look at the crystallography and find out what is that plane which is perpendicular to the 111 plane. If you look at that particular plane, that and consider what is perpendicular to the 111 plane of the TiB2, what is perpendicular to the 111 plane of TiB2, which are basically the side planes, basal plane and the planes which are side, which are basically of the type of 1,1,1 type of planes, you can look at them. So if you look at those planes, that means what I am talking about is if you think of, so these planes are perpendicular to this plane, these planes are the ones which are perpendicular to this particular plane, and whatever plane which is perpendicular to 111, that may not have a coherency, these two planes may not have a coherency. As a result, on the two sides of this aluminum you may not see any coherency unless both of them are cubic. If this is cubic and that is cubic, this is FCC, that is FCC, then the plane which is perpendicular to 111 plane will definitely have, because both are FCC, you will have this happening. If not, okay, the plane which is perpendicular to 0001 and the plane that is perpendicular to 111 may not have coherency, and as a result this particular part will be incoherent. So it will nucleate there and then grow. But in actually in a liquid to solid transformation, the aluminum which is nucleating on the TiB2, you do not see it as a growing as plates, basically because of this, because this nucleation is and growth is taking place at temperature just below the melting point. At that temperature the diffusivities are very, very high. So as a result, ultimately aluminum grows like a grain, equiaxed grain on a TiB2 particles. Whereas if you look at low temperatures where such a nucleation has taken place, at a low temperatures it is easier for it to grow in this direction rather than to grow in that direction. If it has to go in that direction, continuously you need to have a maintenance of the coherency. Clear? Okay. So this is what you would see in so with that more or less we have understood eutectoid.
In iron carbon alloys, we are getting chunky carpets because of the interfacial energy of cement and carbon.
Yes, that is not in eutectoid. Please, eutectic. Yes, tell me.
The same interfacial energy, the logic has to be applied for eutectoid also. Why we are getting a plate?
Yes. The reason is because it is a solid state. You have to consider the strain also here. You have to consider the strain also, and if you consider the strain, and particularly because there you are talking of nucleation of the cementite inside the liquid, is not it. The symmetry, if you consider a eutectic composition, let us say 4.3% composition, it is forming inside the liquid. Here it is forming inside the gamma. If it is forming inside the gamma, then you need to consider what is that interfacial energy. So that means I have to consider the gamma alpha interfacial energy and gamma cementite interfacial energy and then alpha cementite interfacial energy. These are the 3 interfacial energy I should bother. In that case, what I have bothered is liquid Fe3C interfacial energy and then liquid the whatever alpha gamma interfacial energy and gamma Fe3C interfacial energy. These are the 3 there. So there, if you consider that this was lower, and here if you consider this is lower, that is it, as simple as that. It looks at which is the lower interfacial energy, and so whichever is the lower it would happen. So and one more thing is, once it nucleates, how it grows as chunky or not, it depends on the growth rates. That is what I have just now said. Some of them would grow as needles. There are number of cases in eutectics where you have needle like microstructures or rod like microstructures. Aluminum silicon is an example. There are also examples of lamellar eutectics, isn't it? You have aluminum copper is an example where you have lamellar eutectics. So where you see this kind of a situation coming into picture, that this is lower energy than this or this. So as a result you would see that happening. That means 2 solid interfacial energies are lower. Okay. In aluminum copper 2 solid interfacial energies are lower, basically because both are if you consider, one is a theta phase which is actually orthorhombic and alpha is the cubic, but there is, if you look at high temperatures, the interfacial energies of both of them are close to each other, and as a result they can come out as in fact theta is not even orthorhombic, it is BCT, it is tetragonal, sorry, orthorhombic is Fe3C. So tetragonal structure has correlation with a cubic structure, excepting the C axis, everything else is similar. In fact you take a cubic, pull it, that is how you get a tetragonal structure. So that is how you can see that there is a possibility of alpha theta lamellar eutectic coming, that is how you get a lamellar eutectic, whereas here you cannot get a lamellar eutectic because gamma and orthorhombic there is no correlation, and compositions are also entirely different. As a result you will not see a possibility of a lamellar there. Okay. When do you say interfacial energy is lower? Interfacial energy lower when the structures are similar. For example, Ni3Al nucleating in a gamma phase, we say it forms very easily because the structures are similar. If the structures are not similar, the interfacial energies cannot be. In fact, if you see that eutectic where you would see both the phases that are coming out are cubic, let us say, you would definitely invariably end up in lamellar eutectics, because the interfacial energies will be similar. For example, if I take a copper silver eutectic, copper silver eutectic will definitely be lamellar, if you go back and see, because both are FCC and there are no intermetallics in that phase diagram at all. It is a simple eutectic phase diagram. Okay.
Do we see reversed eutectoid?
If you want to call it as a divorced eutectoid, in principle binite is a divorced eutectoid, is not it? There is no lamellar structure. So it depends on where you are having the actually interesting question. We do not call it actually as eutectoid because it is not happening, in fact if that is the case, the cementite formation, eutectic reaction, where cementite is coming out first and the remaining liquid is becoming gamma, can I call this as eutectic? Because both of them are not forming at the same time. So ultimately you have to see the final microstructure, liquid giving 2 solids finally. So if you look at it, the gamma giving 2 solids finally, one is a ferrite, another is this one. In fact we talked about it even in peritectic reaction. Peritectic reaction is finished the moment a peritectic layer is formed, there is no more peritectic. You think of this case of liquid plus delta giving you gamma, the moment gamma forms on the delta, where is the peritectic reaction? But at the same time liquid and gamma will delta will vanish and finally you will get gamma. How does this happen? We said this happens because of the diffusion. Do I call this as peritectic reaction? So we call it as peritectic transformation and solve our problem. Isn't it? So that is what it is. So in principle a bainite can be called as a eutectoid. It is only semantics, it is only how you look at it. Finally you have, but if you look at it, the whole transformation is first the gamma is giving you alpha of a same composition, which is a polymorphous type of a transformation, and from polymorphous transformed alpha cementite is precipitating out. That is what is the actual transformation that is taking place. So in principle it is from that point of view it is not actually eutectoid, but it is ultimately the mixture is alpha plus cementite mixture with a different morphology. Okay. Anything else?
Bainite formation, the ferrite is the active nucleus.
Yes.
And the ferrite, the eutectoid, it is the ferrite formation, it is the cementite. Why is there a difference?
Very again it is not very difficult to understand. See, if you look at the two transformations, gamma giving perlite, gamma giving bainite. In gamma giving bainite we have undercooled to such an extent that the carbon is not able to move much. Because carbon is not able to move much, long range diffusion, short range possibly it can still do, long range diffusion is difficult. As a result gamma first becomes alpha of the same composition, polymorphous. Here the carbon is able to move. So what happens is carbon would come to the grain boundaries of gamma and form a small regions of enriched carbon. Once that enriched carbon region reaches that of 6.67 or 25 atoms out of 75, initially the number of atoms of carbon is very small, it is 0.8, that is weight percent. If I convert it into atomic percent, you would get still possibly about 2 or 3. So 3 atoms or 4 atoms of carbon in 100 atoms of iron, okay, something like that. That is the initial state. From that initial state more carbon atoms come from a different region, and so that region becomes 25 atoms, then you can easily form nucleus. That is the reason why, and carbon can happily move at temperatures closer to 723. So that is the reason why cementite is a nucleus there, whereas here cementite is not able to be a nucleus, carbon is not able to move. And if you further go down you get martensite, because even that small short range diffusion that we can see there is not able to happen, and finally you get a diffusionless. Tomorrow we will talk about this. Okay. Anything else?
To improve the diffusivity of an atom, particular atom in a system, other than thermal activation, is there any other possibility?
Yes, you introduce certain let us say vacancies. There are people who have done by, okay, somebody may say that all are interrelated. For example, if I do irradiation or if I do ball milling, I do a lot of, let us say I take gamma, I austenite powder and do ball milling. I introduce a lot of defects into it, dislocations. Then the moment there are large number of dislocations, you have what is called pipe diffusion. Have you heard of it? Pipe diffusion means diffusion through the dislocation core. Dislocation is nothing but a row of vacancies, isn't it? So if you introduce large number of dislocations, then the diffusivity can be increased. So that is the reason why many in ball milling, many reactions that can happen, that usually are supposed to happen at high temperatures, can happen at low temperatures. Another thing is you make them nano, you introduce large surfaces, then reactions can happen. For example, a simple example I can give you, aluminum plus Fe3 Fe2O3, if you take iron oxide plus aluminum, there is a reduction reaction. What do we call this? Metallothermic aluminothermic reduction, Thermit reaction people call it. This usually occurs above the melting point of aluminum. The same thing can occur much below the melting point of aluminum the moment you make both of them nano. This is what we see in ball milling. You take iron oxide and plus aluminum mixture, put it into a ball mill it, after some time at room temperature you see this reaction happening at low temperatures, just because you have enhanced the diffusivities, because surface diffusion can happen now and diffusion through the dislocations can happen. These are other ways. We will stop now.